Welcome back. In today's session, we are analyzing a foundational problem in semiconductor electronics, focusing on a silicon bar under equilibrium conditions at room temperature. Let's read the problem statement together. A silicon bar is doped with donor impurities, capital N subscript D, equal to 2.25 times 10 to the power of 15 atoms per cubic centimeter. The problem also specifies that the intrinsic carrier concentration of silicon at 300 Kelvin is 1.5 times 10 to the power of 10 per cubic centimeter. Our objective is to determine the equilibrium electron and hole concentrations under the assumption of complete impurity ionization. Take a moment to note down the given parameters displayed on the left of your screen before we proceed to the core physics. Now, let's look at the underlying principles. We are dealing with an N-type semiconductor because it is doped with donor impurities. The assumption of complete impurity ionization means that every single donor atom we added successfully contributes exactly one free electron to the conduction band. Therefore, the equilibrium electron concentration, which we denote as small n subscript 0, is simply equal to the donor concentration, capital N d. To find the minority carriers, which are the holes, we must rely on the mass action law. This fundamental law states that the product of the equilibrium electron and hole concentrations is always a constant at a given temperature equal to the square of the intrinsic carrier concentration. By isolating our unknown variable, we find that the hole concentration, P subscript 0 equals Ni squared divided by the electron concentration. Let's substitute our numbers into the formula to execute the final calculation. For the numerator, we square our intrinsic carrier concentration of 1.5 times 10 to the power of 10. This yields 2.25 times 10 to the power of 20. For the denominator, we plug in our electron concentration, which is 2.25 times 10 to the power of 15. As you can see on the right side, the constants 2.25 elegantly cancel out. Subtracting the exponents leaves us with 10 to the power of 5. Thus, our final hole concentration is exactly 1 times 10 to the power of 5 per cubic centimeter. This confirms that option D is the correct answer for this examination problem. Notice how the majority carrier concentration remains massively higher than the minority carrier concentration.